Yeah, so in this case, we only need 20, right? But we have 21, but it is okay because at least 20 numbers are satisfied, then we are okay. So this number 80 satisfies these two. What about 81? Does 81 satisfy both conditions in this case? So the second one, equal to or greater than 81. The total number of it is just 20. So that satisfies the second condition. And then what about the first one? So we need to at least have 80 data items less than or equal to. So we have an 81. So the total number of data items satisfying this first condition is 81, right? So 81 also satisfies these two, right? So in these cases, we have these two choices. Okay, so in this case, we just take the average of these two. So if you remember the case where we have to compute the mode, the median value, but if we have an even number, maybe 4 numbers, then we have, we don't have exact single number as a median, right? So in that case, we just take the average between these two middle numbers. So in this case, we have, similarly, these two choices and take the average between them. So that's our 80% percentile. And let's look at another example. Usually in maybe 80%, and then if the number is this 22, for example, and in this case, if we just compute these number, and then this number is no longer an integer, right? So we have to pick up 17.6 ranked number out of 22 number. So we sort them in an increasing order, and then we have to pick up 17.6 ranked one, right? So in this case, we can only choose 17th or 18th because these two are the existing data items that we can pick up, right? Okay, so in this case, the conclusion here is the answer that satisfies those two conditions are this 18th number. So let's check that. So from the previous condition or requirement, NP here is computed as a 17.6. So 17.6 number of data items should be equal to or greater than the selected number. Okay, so if we select 17th ranked number, and then we only have 17 data items that satisfies this, right? So that way we have to at least select 18th number, right? That way we need to have at least 17.6 numbers satisfying the first condition, right? So that means we have to have 80. So this number is 80. 18. Okay, because it should be at least 17.6, but we have only the option of an integer because we only consider the count of the data item. So in order to satisfy that, we need to have 80 items satisfying that. Okay, so at least the item should be 18th ranked or higher ranked, right? And then let's check the next one, and 22 times 0.2, which means 4.4. So we have to have 4.4 or more data items that satisfies the second condition, which means you have to have at least 5 data items satisfying this, right? And then let's think about 18th data item, and then the number should be equal to or greater than this 18. So we can count it starting from 18, right? 18, 19, 20, 21, and 22. So 18th ranked data item satisfies the second conditions as well. Okay. So in summary or in conclusion, we just compute, these two multiplication or product of these numbers, and then just do the ceiling of this number. If it was a 17.1 or 17.6, and then we just simply pick up the 18th ranked number. And then among these percentile, there are some particular example that we frequently use. So that is called this quartile. Quartile means, quarter is like 1/4, right? So quarter to the 5. So if we say that, then what time is that? Quarter to the 5. Is it quarter to the 5 is 4:45, right? Because 5 minus 15 minutes. Right? But anyways, so quarter means 1/4. So quartile means like 25 percentile. Okay, and that is especially called the first quartile. And then what about the second quartile? So 50% percentile, right? And then third one is 75, right? Then sorry for the Korean slide, and I just shamelessly copied and pasted from some other professors' slides in Korean University, probably in the math department, I guess. But I thought, this one is quite comprehensive to understand this box. So let me just show this kind of example. So if you happen to do some data analysis, like machine learning, data mining, and so on, probably you may be able to use, or you may want to use this kind of a graph to show your method is really better than the other. So suppose you just conducted some experiments, and then within one experiment, due to many variations within the same settings of an experiment, there may be some different numbers that you can observe as your maybe accuracy or any kind of performance. Sometimes, so we collected some accuracy of diagnosing a certain disease, like diabetes, probability or accuracy of correctly diagnosing a disease, and then using a particular maybe MRI device, which costs maybe 100,000 won, which is really expensive, for example. I'm not sure if it's expensive, but anyways. So in that case, the hospital A, B, and C, and D, so suppose we collected their accuracy value. And then we can think of those accuracy values as the performances for this particular device, because all the hospitals use this particular devices. And then let's consider another device, another MRI device, which is much cheaper than that. Okay? And then suppose we also deploy those devices to these hospitals, and then suppose we collected those accuracies. And because it's cheaper and it's a less, performance is less, or it's not very good, so the accuracy might be a little lower than that. Right? And so we can consider the distribution of these two cases. Then, are they really clearly different, or they're roughly the same, but with a very small or minor differences? So we want to do this kind of analysis. So this kind of box plot is often used for that purpose. So suppose this one is the samples or the observations from one case, and then the other, and so on. Right? So so let's study what these mean. Okay, so for one box plot, this one is inside of our rectangle is our median value. Okay, this is a median, or this one is like 50% percentile. And then this one is 75% percentile, or the third quartile, right? Third quartile, and then the first quartile. Okay, So that way we form this rectangle. And then the range between them. So suppose we collected some person's height, and then the first quartile is maybe 165, and 75% percentile or third quartile is maybe 180. Okay. And then we can just subtract these two values, and that value is 15 centimeter, right? This 15 centimeter is called interquartile range. So approximately about 50% of people are falling in this range of height. Okay? That is what this means. Okay, and then let's study these two narrow lines. So how do we represent the length of, how do we determine the length of this line? We computed this interquartile range, which is a 15 centimeter. And then we multiply it with 1.5. Okay, 1.5. The number is not very good, but it's 22 centimeter 0.5, yes. Right? So we add 22.5 centimeter, which is this guy times 1.5, right? And then among them, we consider the maximum value that we actually observed. So this is just a range, which is 202.5. So that is our maximum possible range. But in reality, in our sample, we may have observed that particular value, or in other cases, we may have observed a little less than that. I mean, just to filter out or recollect those data items less than 202.5. Okay, and then we can pick up the maximum value that we actually observed from our data. So that may not be exactly the same as that value, right? Okay. So that way, within that range, we select the value that was actually observed, and that value, that actually observed value is representing the length of that line segment. Okay. And then we do the same thing on the lower part. So 165 minus 22.5. Okay. So that is what this means, right? So, and then using that as a kind of lower side of a threshold, so we consider only the data that is higher than that or larger than that, and then pick up the minimum one that we actually observed. Right? Then that value is represented as that line segment. Okay, and then still 202.5 centimeter or less. Yes, suppose that was somewhere around here, but the actually observed one, that was the maximum value within that range, was maybe 198 centimeter. Okay, and then we can observe. We can of course we may have some other data that are outside of this range, which are really larger than this 202.5. We may have such kind of data, which is considered as really extreme value or very rare value, really tall value. Okay, and then for those guys, we just represent each of them because they are really important in our life. So we can actually maybe count them one by one. So how many people are there that are taller than maybe 200 and 2 meters. So in those cases, yeah, we can just count it because there are so small number of them. Right? So those cases, we actually just draw those individual points outside of those interquartile, and those this outside of this value. Okay, so that is represented by these actual points. Does it make sense? Any questions? In this case, let me ask the question: where is the mean then? Can you tell me where the mean is? So I mentioned that the single line inside the rectangle is a median, not a mean. So what about the mean? What about the mean? Would it be some like this kind of middle line? Will it be true? Is that our mean or not? Yeah, we cannot guarantee, right? So in general, in this box plot, it doesn't show mean. Okay. So, but yeah, there are many other kind of rich kind of information to get some idea about our data. So yeah, so you can understand now what this box plot is, right? Then from this box plot, yeah, roughly those median values are placed somewhere in the middle of our rectangle. But what about like this case, where so for sure within this range or within this height of this box is containing 50% of the middle data, right? Because then the first one is the first quartile and the third quartile. And then the median is somewhere there. What does that mean? What does that mean? So suppose we have 100 points or 100 data items. Then 50 of them should be placed inside of here. Right? Then suppose we have we observe the median here. And that means half of our data, or 25 data items, should be just placed here, crunching them all. Right? That's what this means. Right? That's what kind of we can understand. Right? In this case, if we think about the histogram or the probability distribution, right? These are the possible values. And then we can think about some kind of histogram, which is drawn horizontally. In that case, it will be something like this. It is a little bit smooth shape, then very, very sharp. Then, yeah. So yeah, we can kind of infer their original histograms. Okay, so yeah, let me get back here later. And so this is called a skewness of the data. Skewness. So yeah, you guys know the normal distribution, right? Or Gaussian distribution, which has a shape of a single mountain, and the mountain is really symmetric. So if we mirror them, they should be approximately the same. So that is the one characteristic of our normal data or normal distribution. And then in this case, although yeah, it is not exactly a normal, but it can be considered as approximately normal. And then this guy is called a skew data, and so let's just think about this part. Let's focus on the right part. And then if it was really symmetric, then the distribution should be also this kind of sharp, right? It should sharply decrease, right? But compared to the right side, it has a little bit smoother decrease, which reaches much farther to the left. Okay, which reaches much farther to the left. So that is called a left skewed. Then this is called also. So this part that shouldn't have reached that far. Okay? I mean, from the perspective of our right side. So these are kind of unexpected patterns, right? So if we believe or if we think that our distribution should be more like right side, then those parts is a little bit undesirable kind of data pattern. Right? Yes. But anyways, that is called related to that left skewed. So that is called the left skewed. And also it is in this kind of distribution it is also called it can be considered as like tail. It is not directly related to our study or our material, but it is called a long tail. It's called a long tail distribution as well. Okay. But anyways, if you happen to see those kind of word long tail distribution and things like that, especially in machine learning and data science or data mining and so on, that is usually meaning like a bad thing or some kind of challenge that we have to carefully deal with. So those kind of things are actually messing up our proper training of our model and so on. So that is the meaning of this long tail distribution. But anyways, you got the idea about this left skewness. And also the opposite case is called a right skewness, right? Then, if you want to verify or if you want to judge whether your data is following the normal distribution or not, okay, then we need to have a particular rule, right? So in this figure, it looks like a normal, but it's not exactly normal, right? So why is it not normal? I mean, when can we rigorously say that this is not following the normal? Or some other cases, how can we say our distribution is normal based on a very well-principled criteria? What is our criteria to determine that? So empirically or in practice, we apply these kind of rules. So I'm not sure if we studied the S, which is called a sample standard deviation. But the standard deviation, you guys studied the sample variance. We studied the sample variance. We just compute the variance, right? And we just take the square root of it, and then that is called a sample standard deviation, and also it has a particular name of standard deviation. There is standard deviation, and then from our data we compute our standard deviation, and then we can have something like interquartile length rate, where we have a mean value, and then we add standard deviation on the positive side and the negative side, right? And then we can have this kind of range, and then we count the relative count of data items that are falling into this range, right? And then how many data items are there relatively, and if approximately 68% of them are contained in those range, and also we extend this range by covering two standard deviations away from the mean or center. So if that range contains 95%, okay, that is, in that case, approximately those three are satisfied, and then we call our distribution the normal distribution. And we don't use this in general, but if you remember what we learned in high school, mu plus 1.96 sigma and minus mu minus 1.96 sigma. And what was the probability of it? It is 95%, right? So we studied something like this, right? So it is exactly the same rule as the second rule, right? So 1.96 is approximately 2, right? Yeah. So in that range, you should approximately have 95% of our data based on the Gaussian distribution. Then what if we change these values into 1? Okay, if we look up our probability distribution table, so I think yeah, you had some table on the back of your math book or textbook. There were all the tables about the cumulative distribution of the normal distribution and so on. And so in that case, if we compute that, the probability of that range is approximately 68%. If we extend it to the 3 similarly, it's 99%, 0.87%. Okay, and then in this case, it is not, yeah, it is clearly not following the normal distribution because it has a true mountain. So in the Gaussian distribution, you have to have one single peak, right? And then also it should be symmetric and so on. In this case, we have a 2 peaks, right? So in that case, it's called a bimodal data. Then bimodal means your data has 2 modes. Okay, so the adjective form of a mode is bimodal. Okay, so mode. So in this case, what was the mode? So mode was the data value that has the highest frequency. That appeared most frequently. So that was the definition of the mode. Right? So in the histogram, what is the mode? So yeah, so let me ask the question from this evening. What is the mode? Where is our mode? Maybe the value is 1, 2, 3, 4, 5, 6, 7, 8, and so on. Then what will be our mode? It should be 6, right? 6. Yeah. So yeah, it's still in this case we have only one single mode, right? But approximately, if we think about this, the meaning of this mode as the value that has this kind of peak, okay? And then you can think of it as having a true mode, right? So that mode is this value, and then 8, 10, 9, 10, 11, 12. So 6 and 12 is our mode. Okay, then in this case, then, okay, so let me, get back to this field data. So where is the mode? Mode is somewhere here, right? So this is our mode. And then where will be the mean? Is mean right or left to that one? Mean value. Mean value should be left, right? Left. And then, median maybe place somewhere around the median. Okay. And how do we determine, or how do we get the idea of why the mean value should be to the right of that value? How can we judge it? What is our logical thoughts? I mean, what is the reason for such conclusion? Yeah, so we will study like probability distribution or density thing, and then if we have a density, then this is our definition of mean, right? So it's like, in the case of discrete value, xi and p of xi, right? So suppose we have the dice having 1, 2, 3, 4, 5, 6. So those are possible values, and then it has a probability value associated with it. Okay? And then suppose our dice is really carefully crafted by some shady like casino and so on. So this, yeah, the probability is 1, 6, and 1, 6, and 2, 6, and 0, and 2, 6, and also 0. Okay. Anyway, from here you can, you know how to compute the mean value or expectation value. You just multiply 1 times the 6 and then add to the 2 times and so on. Right? And then it's a continuous version. It's this, right? And then those probability value or probability, that is called the probability mass function, and that is actually almost the same as our histogram, right? So in our histogram, 1, 2, 3, 4, 5, 6. Yeah, 1, 6, 1, 6, and 0, and 2, 6, and 0. 1, 2. Let me change this. Okay. Yeah, something like that. Okay. So that is our probability mass function, and that is, if we do like many number of trials of rolling a dice, and then count the numbers, and then draw this histogram. And then if we do this kind of rolling a dice infinite number of times, and then that histogram should be the same as that true probability distribution. Right? But anyways, from there, the mean value of this, you know how to compute that, right? But intuitively, the mean value is in this graph. The mean value is corresponding to the value that divides the area of this mountain exactly into half. So the area of this mountain split in half by our mean line, those areas should be equal if that splitting line is our mean. Okay, so this part and this part, the area should be the same. So that is a property of our mean. And you can easily prove that by using probably we will study that later. In the later lectures. But anyways, okay, then let's study this Chebyshev inequality. This inequality is So let me explain that. So we consider the mean value and standard deviation S, and then similar to checking whether the distribution is Gaussian or not, we considered the mean, the range of the data items of mu plus, for example, 2 times sigma or 2 times S, mu plus 2 times S. Oops, should be minus, right? Okay, then we do the same thing of counting compute the relative counting or relative frequency of our data items falling into this region. We have a center as a mean, and we have some range deviated by our 2 times the standard deviation. Then we consider or we count the relative count. So that relative count is represented as this. So SK is those data items falling in this range. Okay? Then that is set or 집합이죠. And then what is this? What is this operator? is representing the number of elements of our set. And that also has a special name. Does anyone know the name of it? It's called, it has really nice and fancy name. It's cardinality. Cardinality. Yeah, so it is called cardinality, and it's exactly the same as the number of elements in a given set. Anyways, so this part is the number of elements in our set, and then divided by the total number of data items. So that is the relative count or relative frequency of data items falling into this category. And so here this Chebyshev inequality is saying that we don't care the true distribution of our data, whether it's a Gaussian or a binomial or any other distribution. We don't care about the particular distribution that our data has. Okay? So it is a universally true. Okay? So it is true all the time, for regardless of any distribution. And the message of this inequality is saying that that number, okay, falling into this range, that number, relative number, is always greater than, or greater than this number. So what is k? K is this value, 2. And then when it was 2, and then it is saying 1 minus, so right? So it is like, it is 75%. So regardless of any distribution, okay, so if you set 2 and then look at the range of u plus 2s minus 2s, then the data items falling into this range is at least 75%. So that is important. And then if we narrow down this, if we decrease the range as maybe u plus s, just 1 times s, minus 1 times s, we have a smaller range, and then naturally the data, relative data items will be smaller, and then still, even if it's smaller, but it should have, it is at least, it's 0, right? So in that case, we cannot apply that. And then if we have a 1.5, and then 1.5 squared, so it's 225, right? So it's like around 60%, right? So so this is the minimum number that we can guarantee, okay? For those data items falling into this way. So let's try to violate this rule. Okay, just intuitively, we want to violate this rule. So we set this range, then we put as much data as possible to outside the range, because we want to make it false. Okay, then that kind of distribution, so I just imagine one example of such kind of distribution is something like this, right? We have a mean here, right? So we put as much data as possible to further extend, okay? But still, this inequality says, okay, so you cannot violate this rule. Okay? So in that case, why it cannot be violated? So in that case, the range is bigger and bigger because our sample variance S, okay, sample variance S will be larger. Will become larger correspondingly, right? Okay. So we have some proof of this. Okay, so let's prove that, very quickly. And this sample variance is defined by this divided by n minus 1, right? And then we can multiply it here. And then this part, which involves all the data items, okay? And then compute the differences from the mean value, and then take the square of it, and then sum them up. And then those terms will be, so suppose we have 100 data items, and then we will have 100 such terms, right? And then we can divide them, or we can partition them into two parts, where those data, the first one contains those data items falling into this range, and the other remaining data that are outside of this range, right? So that is what we did here. We split them into those falling into this or outside of this. And then we simply just remove them. And then it is sum of some squared value. So that's positive. Right? And so the total sum, out of the total sum, we took out some positive part, so the value will be small. Right? So that's where we have this inequality sign here. Okay, and then here, let's think about this value. So those values are outside of our range. So the minimum distance from the mean value to each of the data points will be at least 2s. Because by definition, that set is those data items outside of our range. So this difference is at least, or the minimum value of this distance will be 2s, or in this case, ks, when we say 2sk. Okay? So this one is a minimum value, minimum possible value for each data item outside of our range. Right? Then we just plug that minimum value, and then that value will be the smallest possible. But in practice, sum will be bigger than that, right? Okay, so in that case, we can just replace this guy as this, and then we can further introduce like this inequality sign, right? Then, yeah. And then here, we have to sum them up. Sum these constant values. And then how many data items are there? N minus the cardinality of sk, right? That is the total number that is corresponding to this summation sign. And so if we just manipulate them, then we obtain this. And so, yeah, obtain this. Okay. so the time's up. So, yeah. So that is how we prove this. Yeah, let's continue next Tuesday. Thank you very much. 그러네요. 그냥 확인해. 하면 돼.
So I said, last time we did but we confirmed we did that was my dream. So I don't know if there is but in the option, so I can just start right now.
So you have
they just told me to have joined it.
I think that there are some
Oh yeah, because it didn't say.
영지야.
여기서 레인지가
네.
최소값에서 최대값까지 근데 이게 그 여기 있는 그 이상점 이거는 포함하지 않는 거예요.
이게 박스플랫을 좀 아까처럼 좀 더 복잡하게 그리는 버전이 있고요. 아마 좀 더 쉽게 그리는 버전이 있거든요. 그래서 좀 쉽게 그리는 버전은 그냥 여기서 쭉 그냥 맥스 그다음에 이제 미니멈 밸류로 쭉쭉 하는 게 하나가 있고, 근데 아마 그렇게 이거는 지금 그렇게 그린 거 맞나요?
그러니까 지금 여기는 이 뒤에 뭐가 더 있는지 없는지가 몰라서 그런데
그거는 그러니까 여기서 그렸을 때는요 좀 쉬운 버전의 박스 플랫인 셈이고요.
그 이상점이 표현되는 거에서는 레인지가 이상점까지 끝까지 완전 끝까지
이상점이 포함되는 버전에서는 이 라인이 데이터에서 발생되는 맥스 값까지 가지 않고 아까 얘기했던 그 인터쿼탈 레인지의 이제 1.5배 한 그만큼까지 갔을 때의 실제 발견된 데이터의 최대값까지 라인을 그려줘요.
선이 그려지는 데까지만.
근데 이제 그거 이상으로도 데이터가 있을 수도 있죠. 그래서 그것들은 여기서 이야기한 아웃라이어 혹은 이상점으로 점으로 뭐 이렇게 표시했던 거였고요. 근데 그런 버전의 박스플랫에서도 사실 이런 아웃라이어가 없을 수도 있어요. 그러니까 인터쿼탈 레인지에 데이터의 발견된 데이터의 최대값이 이 안에 다 들어올 수도 있거든요. 그렇죠? 그러니까 실제로 이렇게 계산해봤더니 이렇게 나왔는데 2m 넘는 사람이 이 세상에 한 명도 없어요. 그러면 사실 내가 이 바깥쪽에 찍으려고는 했는데 찍을 포인트가 없는 거죠. 그렇게도 그려질 수가 있고요. 그렇게 되면 여기서 실제로 그려지는 포인트 자체는 데이터가 가지고 있는 가장 최대점이 되겠죠. 그러니까 이 라인의 크기 자체가.
그럼 그냥 데이터와 최대 데이터가 어디 있냐에 따라서 달라져요.
네. 그래서 데이터가 이 인터쿼탈 레인지 플러스 곱하기 1.5배 한 그 시점에 바깥쪽에 있어서 삐져나오면 이제 거기를 찍어주고 거기부터 그러니까 여기 이상부터 우리가 찍도록 하는 거야. 하나하나를.
그러니까 찍는 거는 그런 건데.
네.
레인지를 어디부터?
이 레인지요? 이 레인지?
그러니까 레인지가 그
네.
최대 값에서 최소 값까지의 뺀 그 거리.
그러니까 여기 레인지는 이제 25등과 75등을 구해서
그건 인터컨트롤.
네, 그거에 여기 보듯이 이제 그거 1.5배를 해주죠.
네. 그래서
여기서 이제 15cm가 나왔으니까 180에서 1.5에 그러니까 15cm 1.5배를 한 22.5cm를 더해서 202.5까지를 레인지를 일단 딱 잡는 거예요. 그래서 데이터 중에서 이거 안쪽으로 들어온 애 중에 가장 큰 놈까지의 라인을 그려주고요. 거기까지 라인을 그려주고 실제로 데이터가 이제 뭐 한 198이 발견됐다가 또 205cm가 발견이 됐어요. 그러면 여기 이렇게 그 다음부터 찍어줍니다. 그래서 이 어떤 threshold 점으로 그려주느냐 아니면 선으로 그려주느냐가 이 값에서 1.5배 곱하기 1.5배 이제 인터쿼탈 레인지가 되는 거예요. 여러 개 찍을 수 있죠. 그러니까 아까 뭔가 헤비 테일드, 그러니까 뭔가 좀 디스트리뷰션 쭉 저 끝까지 가요 뭔가. 그러면 뭐 여기에 이렇게 잔뜩 몰려 있었는데 인터쿼탈 레인지 해갖고 이제 1.5배 해갖고 늘려도 거기 이상으로 삐져 나오는 데이터들이 많은 거예요. 그럼 걔네들은 점이 많이 찍히겠죠.
최대값까지 전까지의 점만 있으면 거기까지 거예요.
네, 그 최대값은 정확하게 최대값은 아니고 이 인터쿼탈 레인지가 지금 15cm라고 했으니까 180에서 15cm 곱하기 1.5배를 한 202.5. 거기까지 선을 긋는 게 아니라 네, 그 레인지에서 그 밑에 있는 애들 중에 데이터 중에서 가장 컸던 놈까지를 라인을 그려주고요. 그렇죠. 그래서 여기까지 쭉 매번 그려지느냐 그렇게 되면 사실 의미가 없어요. 왜냐하면 15cm면 위로 22.5cm를 그냥 쭉 그려주고 아래로 쭉 그려주면 그냥 그리면 되는 거죠. 데이터에 디펜던트한 게 전혀 아니니까. 그래서 저 라인의 실제 길이는 이해가요?
여기서 나온 거는 실제로 그 202.5까지가 발견됐기 때문에.
그러니까 여기서 이제 202.5는요. 202.5는 여기가 정확하게 202.5가 아니라요. 한 여기쯤 되는 거예요. 그리고 네, 202.5가 여기고 그 다음엔 202.5 밑에 데이터들 중에 가장 큰 놈까지가 뭐 한 198이었다. 우리가 라인을 198까지만 그리는 거예요.
근데 그러니까 만약에 그 데이터 중에서 가장 큰 값이 그러니까 202.5가 나오면
거기까지 그려지는 거예요.
여기까지 그려지는 거고. 그러면 이것만 보고는 그 이제 그 끝이 202.5인지 그거보다 좀 작은지 그거는 이것만 보고는
모르죠. 그렇지만 202.5의 밑에 부분에서 가장 큰 놈이 누구다라는 걸 보여줍니다.
그러면 저 끝은 많아야 202.5다라고.
그렇죠. 많아야 200.5.
그러면 저게 그어졌다는 게 발견이 지금까지 된 것만 생각하는
그렇죠.
거고.
된 것만 생각하는 거예요. 네.
근데 발견이 됐다는 거랑 존재하는 거랑 좀 다른.
아, 실제로 뭐 모집단에서 이제 있는지 없는지는 모르는 건데, 일단 이 막스 플랫이라는 건 어쨌건 우리가 모아놓은 실제 샘플을 가지고 그리는 거거든요.
아, 그러면
그래요. 예, 1시간 15분, 그 내가 확인을 미처 못했는데, 내가, 근데 나도 좀 그렇게 했으면 좋겠어요. 예. 아마 될 거예요. 근데, 사실 지금 6시부터 여기서 수업을 한다면 우리가 안 되는 건데, 여기가 지금 이렇게 없으니까 되는 거라고 봐야겠죠.
그 액츄얼 옵저브 밸류라고 설명해 주신 게
네.
결국엔 그 모집단 아니고 샘플에서 제가
네,
알아낸
샘플에서.
거고 그거는
그렇죠.
그러면 그 202.5보다
작은 가장 큰 값?
작거나
우리가
같을
본-
수도 있고
그렇죠. 같을 수 있어요.
그럼 202.5가 거의 액츄얼리 맥시멈 레인지라고 표현하신 게
그거 왼쪽으로 치우치는데
네.
이게 지금 이렇게 반대로 보는 거예요. 이게
네.
오른쪽
네. 오른쪽 기준으로 했을 때는 얘가 이제 오른쪽에 비해서 더 치우친 거잖아요. 그러니까 두 개의 기준으로 봤을 때 사실 이걸 기준으로 하면 여기가 이렇게 그려져야 되는데 여기는 지나치게 쪼그라든 거죠. 그죠? 그러니까 뭐 상대적인 건데 이제 그러면 어떤 걸 기준으로 하느냐? 더 이제 뭔가 좀 내로하게 나타나는 좀 더 뭔가 집중되어져 있는 부분을 기준으로 삼고 반대로
그 지금 여기 치우쳤다는 게
이 모드 혹은 그 피크 아니면 이 최대값을 중심으로 봤을 때 가우시안으로 생각하면 노이즈 디스트리뷰션으로 생각하면 이게 양쪽이 이제 대칭으로 나와야 되는데 그렇지 못하는 거잖아요. 그럼 어느 게 더 꼬리가 긴 꼬리를 갖고 있냐 이거죠. 네, 그러니까 이제 레프트 스쿨드라고 이제
그냥 긴 꼬리를 갖고 있는 쪽을 치우치는 거다.
그렇게 그냥 정한 상대적으로. 네.
몽크를 중심으로
네.
되게 낮아요.
네.
이만큼 쭉 있어요.
네.
그래도
네, 그렇죠. 여러분 질질질하게 이렇게 좀 가면
중간에 하나 올라오고 바이오.
네?
중간에
바이 모달?
모드가 하나 더 있어요.
그런 거는 그러니까 싱글 모달에서부터 이제 스큐니스를 조금 따지는 그런 것 같고 바이 모달은 좀, 네. 참고로 이 스큐니스가 이게 우리가 그냥 그림 보고 그냥 대충 어떤 건지는 알겠는데 지금 이야기했던 다양한 좀 트릭한 경우들이 많을 수 있잖아요. 그게 맞고 그래
이거 싱글 모드 스타트.
싱글 모드에서 그러니까 그렇게 이해를 하면 되고요. 그 스큐니스에 대해서는 우리가 좀 자세하게 들어가지는 않는데 그 스큐니스를 좀 정의를 하는 식들이 또 따로 있어요. 그러니까 우리가 평균과 분산을 정의하듯이 얼마나 데이터가 균형적이지 않고 한쪽으로 확 치우쳐져 있느냐를 계산할 수 있는 어떤 또 공식이 있거든요.
여기서 혹시 잠깐 올라갔다 생각해봐가지고
뭐 크게 봤을 때 이제 싱글 모드를 선택을 어디에 하느냐 가장 높은 거를 그냥 대승적인 차원에서 하나를 딱 정해서 그걸 기준으로 해야 되지 않을까.
네. 아까 그 치우쳐진 그래서
네.
그 평균 그러니까 윤이 이쪽에 있을 거라는
네.
거를 그 앞에 평균식 이걸로 얘기를 했어요.
네.
이거까지는 이해를 했는데
근데 증명은 안 했죠 사실.
그러니까 이거 다음에가 그러니까
언제 이게 나와요. 증명 다음에 나오기도 하고 그냥 뭐 쉽게 할 수도 있고요. 변수 이렇게 변환하는 거를
그러니까 그 평균이 여기쯤에 있을 거라는 거를
어떻게
이거를
알고요?
가지고 얘기를 하신 거 아니에요?
맞아요.
그래서
네.
이것까지는 대충 알겠는데 그 이게
그러니까 이게
여기 있는 거랑
맞아요. 그러니까 그 부분을 내가 이야기만 두루뭉실하게 정확히 이해가 안 했는데 증명을 해보면 적분에 의해서 결국은 이익이 계산이 되는 거잖아요. 근데 이제 우리가 치환 적분해서 y를 이제 뭐 x-u라고 하는 걸로 해갖고 u는 또 저렇게 정의된다. 그러면 이제 y를 바꿨을 때는요. y 곱하기 fy가 항상 0이 돼요. 왜냐면 그걸 증명을 할 수가 있어서 그러니까 뭐 쉽게 생각하면요. 평균이 있어요. 그 평균은 이 식을 만족을 해요. 그리고 마이너스 무한대에서부터 그 평균까지의 PDF의 적분 혹은 저 FX의 적분 그거와 플러스 이제 뮤부터 플러스 무한대까지의 적분 그거 두 개가 똑같아요. 이거를 이제 민이 저렇게 구해진다는 식을 통해서 유도할 수가 있어요.
지금
어디
네?
어디
지금
그 최근
저기 민 설명할 때 이제
가운데 그
스큐니스 네 맞아요 그거 얘기할 때
그거
뭐 그거 증명할 수 있거든요. 뭐 고등학교 때 했을 수도 있어요. 근데 그거는 어차피 나중에 좀 나올 거예요.
바이모달을
네.
그러니까 그걸 바이모달로 꼭 봐야 된다라는 게 좀
애매할 수 있죠.
그러니까 만약에 이렇게 있으면 그러니까 모드는 원래 정의는 최종값이라서 하나만 되는데 이제 그걸 바이모달로 보면 그 두 번째 나오는 그 공 좀 작은 데라도 거기도 이제 모드로 볼 수 있다라는 거예요. 본다라는 걸 볼 수 있다는 거예요.
그거를 이제 정확하게 이야기하려면 역시 또 뭐 정확하게 정의를 할 수 있는 뭔가가 있어야 되잖아요.
그런 거 있긴 있는데 여기서
그러니까 그거는요. 디스트리뷰션만 보고 이거는 대충 바이모달인 것 같네. 이런 식으로 결정을 눈으로 하는 건 아니고요. 아까 이야기하다 보면 이제 바이모달은 이제 가우시안이 이제 두 개가 있어서 예를 들면 이야기를 못했네요. 뭔가 남자들의 어떤 키의 디스트리뷰션 이런 가우시안 여자들은 평균과 그걸 중심으로 하는 산이 있을 것 같잖아요. 그래서 근데 이제 남자와 여자 우리가 그냥 한때 같이 모아봤어요. 그러면 사실 디스트리뷰션이 저런 식으로 나오거든요. 그래서 저기에는 뭔가 공통된 특성을 나타낸 남자, 여자를 나타낸 게 약간 두 개의 서로 다른 그룹이 뭐가 있는 거예요. 약간 이렇게 되면 그 데이터가 이제 이런 식의 어떤 상이한 특성을 가지는 그룹이 존재한다. 그럴 때 생성하는 모델을 애초에 두 개짜리 봉우리를 가질 수 있는 확률 모델을 정리해서 히스토그램이나 피팅을 맞추는 걸 하는데
바이모달이라고 설명하는 게 모두 그냥 어디서 이 정도 그 깊이에서만 얘기한다면 봉우리를 두 개 가지는 셋이면 데이터 셋이면 바이모달이라고 했다.
자, 하나 뭐 또 이야기를 안 했는데 바이모달이 아니라 봉우리를 또뭐 3개 이상으로 가지고 그냥 트라이 모달도 되고 쿼드 모달도 될 것 같고 그리고 일반적으로 이제 멀티 모달이라고 합니다. 그런 용어는 아마 또 여기저기서 또 많이 또 실제 데이터 분석할 때 나오는 용어라 멀티 모달 데이터. 네.
X가 스탠다드 디비에이션.
네.
그게 정확히 의미하는 게
표준 편차인데 표준 편차가
이번에 표준
네, 스탠다드 디비에이션이 표준이고 디비에이션이 편차라는 거거든요.
이 S마크에서 68%가
좋았어요.
그러니까 사실 제가 1년 전에 이 똑같은 색으로 똑같은 커리큘럼으로 확률을 내놓는 과정을 들어봤는데 이제 그때는 이제 수식 증명 그렇게 해가지고 증명을 확실히 가능성인데 그러니까 깊게는 아니고 알아야 될 것만 하고 거의 수식 증명으로 보는데 이거는 이제 제가 무슨 수업 처음 했거든요. 4학년인데 뭐 학사가 되게 좀 이상해져가지고 정수 무조건 들어야 된다고 해서
그러니까 이거 들어가고 이게 또 쓰는 거예요?
네, 저 통계 수업만 제가 2학기 와서 4번 들었거든요. 수학과 확률 통계 듣고 정통 듣고 평가 확률 듣고 이번에 졸업하려고 무조건 점수 있는 건데
안타깝네요.
이거 그러니까 아는 거라 그러니까 좀 안다고 생각해서 안 듣고 싶었는데 안 들으면 졸업을 못한다고 해가지고
안타깝네요.
책이 있어서 이번에 혹시 수업을 보면 방향을 개념 위주로 하시는 분들.
최대한 좀 그 직관을 좀 집중하게 생각을 하는 편이죠.
그래서 따로 준비하는 게 있어가지고 내가 일단 이걸 열심히 해야 되거든요. 학교를 잘 찾아야 되고
네.
그리고 아는 건데도 불구하고 그 개념 같은 게 또 그냥 1년 전에 까먹거든요. 시간 열심히 같이 리마인드 시켰어요.
네. 어디 보기는 좀 열심히 하는 것 같더라고요. 또 해보세요.
진짜 열심히 했어요.
살기가 참 힘들어져서.